I just wanted to thank Trish Steinhobler as well for inviting me to give this presentation today. I've given versions of this in Pennsylvania and in Maryland and a few other places in the Mid-Atlantic region, kind of just covering kind of what we've seen in terms of climate trends to date and what some of the projections might be for the Mid-Atlantic region. As Melissa said, I work in the Mahantango Creek experimental watersheds. You can see pictured on the title slide the outlet of one of our watersheds in flood. And it's these extremes that we see when we switch kind of from dry to wet to wet again, to from flood to dry to wet. These kind of weather extremes that are kind of of interest to us, and kind of a hallmark of climate change in the region. And so I've divided this presentation into 4 parts. The first part is really kind of leveraging information from the U.S. National Climate Assessment and other national sources to kind of just give you a sense for national trends in climate that we've seen to date. And then we kind of zoom into more of the local level where we've done quite a bit of work in the Mahantango Creek experimental watersheds. It's a watershed in east central Pennsylvania. That's somewhat emblematic of some of the changes we've seen in the Mid-Atlantic region, so I can kind of give you a very local feel for things that we've observed over the past, say, 45 years. Excuse me, I have a cough too, so I apologize if I cough occasionally. I've been battling bronchitis for a couple weeks now. Anyhow, then I kind of use a couple different sources, some downscale climate data, as well as regional climate models and some info from the National Climate Assessment to give you a sense for what projected climate change will look like, not necessarily in Pennsylvania, but across the entire Northeast. I'll zoom into our experimental watersheds from time to time to give you a sense for kind of the downscaled local view of climate projections, but most of these will kind of take a look at the Northeast picture. And then a little bit of information on where you can find more info on viewing climate data online if you're interested. And so let's take a look just kind of at the global picture to start. So the warming of the planet at this point, at least among climate scientists, is unequivocal. Global temperature is now is increasing in lockstep with CO2. So here you can see CO2 concentrations on the yellow line going up from just prior to the Industrial Revolution in 1880, about 280 parts per million. And in 2016, we found ourselves well over 404 parts per million. And when you superimpose the temperature changes that have occurred over that time frame, you can see these are temperature anomalies, basically. So the blue lines are years that were colder than normal, and all the red bars indicate years that were warmer than normal. And you can see as we've gone into the 80s, the 90s, and well into the 2000s that all of our years have been above normal, and basically setting annual temperature records the past 3 years. 2014, 15, and 16 each set annual temperature records for those years. And so you can see how temperatures have increased quite a bit as carbon dioxide concentrations have gone up in the atmosphere. This next slide is meant to kind of give you a better feel for just the long-term changes in CO2 in the atmosphere and kind of the unique time frame in which we find ourselves in terms of carbon dioxide concentrations. This is an 800,000-year look at carbon dioxide levels that have been inferred from ice core data. This is the Vostok ice cores. And you can see that for thousands of years, we really haven't had atmospheric carbon dioxide concentrations above just about 300 parts per million. It's oscillated over several thousand-year periods, but never really crossed that line. So essentially what you see is that the periods of very low CO2 concentrations, so these areas here, these are what are known as, it's basically glacial periods here, where carbon dioxide concentrations are very low. And these higher peaks that we see are interglacial periods that are warmer. And we're currently in an interglacial period, but you can see that, prior to the Industrial Revolution, carbon dioxide concentrations are actually heading down until we started to emit, carbon dioxide and other greenhouse gases. And instead, we've had this huge increase in CO2. And arrow off here. Now, in 1950, we crossed 300 parts per million, and in 2016, we find ourselves at 404, and those concentrations continue to go up even in 2017. So they're even higher at this point in the year than they were last year in 2016. And so you have to go way back to find carbon dioxide concentrations that were similarly high in the atmosphere. In fact, the last time they were that high, 404 parts per million, was 3 million years ago. So we find ourselves in a very unique time period in terms of carbon dioxide concentrations, and that has huge implications for the climate and for the climate system, that is. And so this animation, looks like it was already kind of playing, hopefully it'll play through again, shows kind of how unique 2016 was in terms of temperature records. These are monthly, basically seasonal temperature values, and you can let this animation play through, and you can see all the years that are setting temperature records as we go through in time, and hopefully you'll get a sense for how anomalously warm 2016 was relative to all the years that preceded it. It's the last year that pops up. And so 2016 was a record warm year, and it stands alone when you really look at it relative to other years in the instrumental record. And there are other kind of global records that have been kind of worth paying attention to, different temperature streaks that that folks have been keeping track of. For example, monthly temperature records. You can look at 2015 and 2016. We set all-time monthly temperature records, at least for the instrumental record that goes back to the late 1800s. So May 2015, we set an all-time temperature record, and that continued all the way through August of 2016. And so in May 2016, we actually beat the May 2015 record, and then the same thing happened in June and July. And so we continued to set these all-time temperature records until that ceased in September. So we had a 16 straight month period of these global monthly temperature records being set. So that was kind of unprecedented over the instrumental record of temperature record keeping. Another one that's kind of interest is just the fact that we've had 386 consecutive months if you take February, the last month, February 2017, where temperatures have at least been nominally above the 20th century average. That's saying all these months have been warmer than average. In fact, you have to go back to February of 1985 to find a month that was cooler than the long-term mean. So anybody who was born prior to that has experienced cooler than normal months. I was born in 1975, and so I've experienced cooler than normal months. But anybody who's been born after February 85, all the months have been warmer than normal, and that's likely to continue for March. The numbers aren't in it yet, obviously, because the month has yet to close, but these are likely to continue into the future. And so if you just look at information from the National Climate Assessment, it's pretty clear that temperatures across the U.S. have been rising. These colors just show the temperature trends, how much temperature has changed relative to the 1901 to 1960 average. So if you just kind of highlight the Northeast, you can see the 80s, the 90s, and the 2000s all having warmer than average decades, that is, or warmer than average periods relative to the long-term average. And so temperatures are going up across the U.S. There's lots of ways of looking at this. When you look at it just in terms of summertime temperatures, you can see here how our distribution of temperatures is changing over time. And so what we have is just this bell-shaped curve that kind of represents our normal climate. So if you look at this area here, this is kind of represents our normal climate. These are the mean temperatures here, and the reds can indicate the extremes on either side of the mean, and you can see how the extremes continue to shift towards the red. And so over time, as you move through the 50s, the 60s, the 70s, the 80s, we're shifting more and more to hotter extremes, and we're losing a lot of these colder extremes that we used to experience. So this just shows how our climate is evolving over time, shifting away from cold and moving more towards extreme heat, especially in the summer. And James Hansen has a really nice way of kind of representing this, indicating that if you kind of think of our climate in terms of dice, normal climate would be expressed by two sides blue for cold, two sides white for normal, and two sides red for hot. And so in 1951 to 80, that would probably have been a good way to characterize. You would have equal odds of rolling blue, red, or white. But now in the 21st century, according to James Hansen and his colleagues at NASA's Goddard Space Flight Center, we need 4 red sides to characterize our 21st century climate. That is to say that on any given day or for any given period, you're more likely to roll red than you are to roll blue or white. So we're more than likely to have warmer than normal temperatures than we are to have colder extremes or normals. And another nice way of expressing this is a study that Jerry Meal did, was published in Geophysical Research Letters, just looking at how record highs have been outpacing record lows over time. And so these are data from his study, and it just shows the ratios of record high temperatures to record low temperatures by decade. And you can see in the 1950s, we were about 1 to 1, setting about 1 record high for every 1 record low. The 60s and 70s were a little colder than normal, so actually quite a bit more, were a little bit more record lows than record highs. But then in the 80s, the 90s, and the 2000s, we've had a fairly significant uptick in the ratio of record highs to record lows, with the 2000s seeing a 2 to 1 ratio. So that's 2 record highs for every record low in the 2000s. That ratio is likely to go up for the 2010s. Those data aren't in yet, but I can tell you for February 2017, the month that just ended, for the U.S. as a whole, that record was 116 to 1. So that's 116 record highs for every record low. And that's just for a month. Granted, we'd be averaging these over the period of a decade, so that ratio isn't likely to be that high. But all indications are that 2 to 1 ratio that we saw in the 2000s is likely to go up. And on some of these monthly timescales, especially February, which was just an extraordinarily warm month, nationally and even here in the eastern region, where we hit the 70s and almost 80s really towards the end of the month, we're setting many more record highs and record lows. Another indication of a warming climate. And so as the climate warms, we also see seasons are shifting. So for instance, our growing seasons are getting longer. And for those folks who are either gardeners or farming, there's no doubt that you've experienced longer growing seasons. On average, in the Northeast United States, according to the National Climate Assessment, those growing seasons have gotten longer by 10 days per decade on average throughout the Northeast. And interestingly, hopefully this will start over again. There we go. This animation just shows how fast spring advanced this year. This is spring 2017, showing the advancement of the spring season based on the National Phenology Network, which is using information on various tree and shrub species, their budding and leaf out indicators. And you can see for the eastern U.S., spring was occurring as much as 25 to 30 days ahead of schedule this year. Obviously, this animation ends in March, and that was before the major snowstorm that we saw in the east and the cold snap that we saw afterwards. But this basically kind of classifies as a false spring, where spring occurred much earlier than normal, and then we see a period of days where cold and frost, kind of shut down or kind of slowed spring's advance. And possibly also caused damage to trees and possibly fruit crops and things like that. But this is similar to what happened in 2012 when we had a false spring in 2012. And so these kinds of false springs occur, more regularly with climate change, and this is kind of another hallmark of a changing climate. The animation is actually courtesy of some folks at the New York Times who took the Phenology Network data and were able to animate it. So it's a really nice way of seeing how spring has changed over the years, or for this particular year. In terms of precipitation, we're seeing increases in rainfall in the Northeast as the climate warms, and so you can see the trends in the Northeast, kind of all green to darker green, indicating precipitation increases on the order of anywhere from 10 to almost 15%. These are annual precipitation amounts, so the amount of rainfall we receive in a given year has gone up by anywhere from 10 to as much as 15% in some parts of the Northeast. And we've seen changes in the rainfall extremes too. So not just the total amount of rain we receive in a year, but also just the extremes have changed quite a bit. And the Northeast kind of stands out as a part of the country where we've seen a major increase in the extreme rainfall. Those are the heaviest 1% of daily rainfall events. It's gone up by about 71%. And so we've seen fairly sizable change in extreme rainfalls. And for those from Maryland, for instance, the flash floods that occurred in Ellicott City, among other places in the Northeast, there was Ellicott City floods, there was the West Virginia flash floods on June 23rd, 2016, and then here even in State College, Pennsylvania, we had major flash flooding courtesy of thunderstorms that occurred towards the end of October. I'll show the Ellicott City as an example, and this is an event where very localized but very extreme, anywhere from 5 to 6 to as much as 8 inches. Actually, some local folks with rain gauges reported as much as 8 inches of rain actually in a span of 2 to 3 hours. And when you look at these kind of in the context of monthly rainfall totals, you're talking about anywhere from 2 to 3 months of rain in a 2 to 3 hour time period. And when you look at this using kind of frequency distributions courtesy of NOAA, you'll find that this really is about a 1,000-year storm event with a very low likelihood of occurring in any given year. So very extreme rainfalls caused huge flash flooding in Ellicott City. This is some of the imagery from the floods. These are very rare kind of events, but when they occur, they cause extreme damage. So I mean, whether you're in an urban area where you have this kind of urban flooding, or for those of us in central Pennsylvania, when we had these kind of events this past October that caused landslides, huge amounts of sediment erosion. So folks with, if you were, farming and you got hit with these kind of rains, we had all kinds of major erosion problems. Very difficult to deal with, hard to predict, but another kind of a hallmark of a warming climate. And really, what's going on in terms of, these extreme type rainfall events, they're being driven in part by the fact that the atmosphere now holds more water than it used to. And so this is the consequence of increasing atmospheric temperatures. And there's this really nice physical relationship. It's called the Clausius-Clapeyron relationship. And it's essentially just a water vapor pressure versus temperature relationship. And all that you need to know when you look at this relationship is just that basically the water holding capacity of the atmosphere increases by about 7% for every 1 degree Celsius rise in temperature. And so we've increased atmospheric temperature on average by about 1 degree Celsius, over the past, over the course of the past 100 years. And so essentially that just means more water in the atmosphere, and that means more opportunities for extreme rainfall. There's just more water vapor that the atmosphere can be wrung out of the atmosphere when these kind of storms come along. And so it just, adds to the conditions that kind of support these kind of extreme rainfall events. And so that leads to a really nice quote by Kevin Trenberth, who works for the federal government. He's a federal climate scientist, and he says in this paper about kind of attributing kind of the effects of climate change to extremes, is that the climate is changing. We have a new normal. The environment in which all weather events occur is not what it used to be, and all storms now, without exception, are different. And even if most of them look just like the ones we used to have, they're just not the same. And in part, that's due to the fact that we've increased atmospheric temperatures. There's more water vapor in the atmosphere. The starting conditions for a lot of these storms are just different. And so climate change is playing a role in the occurrence of all these extremes, that we see over the past several years. So I'll take a shift here kind of from the national view and now take a little bit more of a local look, using data from, excuse me, one of our sites in East Central Pennsylvania. And so we're part, our research watershed is part of the Long-Term Agro-Ecosystem Research Network, and it's a national network of USDA sites looking at, not only past changes in, say, climate or hydrology, but also kind of as a sentinel for future changes, in a lot of these conditions. And so we have really 18 sites across the country now. These are federal research sites, and we're the Upper Chesapeake Bay site, and it includes our experimental watershed, which is in East Central Pennsylvania. And so all these sites have long-term data sets from which to draw upon to look at how their sites have changed over time. And that's essentially what we've done here in the Manatanga Creek watershed. We've been collecting data since the 1960s. Precipitation data, they go back to 1968. We've been collecting them past 2012. It's just the trends I'll show, basically go from 68 to 2012. But we continue to collect these data. routinely. So these are 5-minute data sets on precipitation. So same with temperature, but we didn't begin till a little bit later with temperature 1978. So every 5 minutes we have data on atmospheric air temperatures. And stream flow at the outlet, this little yellow triangle at the bottom, that's the outlet of our experimental watershed where we measure how much water comes out of the watershed. So we have a pretty good sense of, with precipitation measurements, how much water is coming in to the basin, and then with stream flow, we can measure how much is coming out. So we can basically kind of do a water balance on the watershed. And so I'll give you a sense for some of the trends that we've seen. A lot of these will dovetail with some of the natural trends I presented earlier, but we're seeing rising temperatures here in our watershed going back to the 60s. Our mean temperature has been going up by about 0.38 degrees Celsius per decade. Our mean maximum temperatures have been increasing as well, and as have the mean minimum temperatures. So all of these are going up. The interesting thing to point out here is that the minimum temperatures are actually going up. You'll note 0.43 degrees Celsius per decade. They're going up faster than the maximum temperatures at 0.35. And so that's a phenomenon that's been seen all across the Northeast and really throughout the country. Faster rising minimum temperatures than maximum temperatures. And part of the reason for that is that clouds have actually changed. We've seen an increase in cloud cover across the eastern U.S., especially at night and particularly in the wintertime. And so the minimum temperatures just don't get as low as they used to most nights when you don't have that radiational cooling from clear skies. And so we're seeing kind of a faster rise in minimum temperatures, and this is kind of this disproportionate change in minimum relative to maximum temperatures is what's known as the diurnal temperature range, and we're seeing changes in this diurnal temperature range throughout the Northeast, not just at our site. And so it really agrees with what others have been observing elsewhere, where people have been monitoring their climates over long time frames. We also see shifting seasons, much like the National Climate Assessment reported for the entire Northeast region. So, for instance, the last freeze date in spring has been getting earlier, and so we're seeing that shift 5.5 days per decade earlier. At the same time, we're seeing the first freeze date in the fall get later, and so with that kind of change happening, it basically implies that our growing seasons are getting longer, and they're extending by about 10 days per decade, which is right in line with what we've seen kind of across the Northeast if you look at what the climate assessment reported. So our growing seasons have gotten longer, and I'm sure folks who are into gardening or for those folks who are farming probably also notice this. And when you get these shifting seasons, you get, excuse me, sometimes you get some kind of, what we saw this year with the fall spring. You can get rapid warm-ups, and so you get a very early start to the spring, and then you can have frost that hits later. So in 2012, I used these slides for the past several years, kind of using 2012 as an example. Of course, now I could probably use 2017 as an even better example because spring essentially started earlier. But in 2012, we saw in our watershed a fairly extended period of record high temperatures that were well into these are shown in Celsius, of course, but these are temperatures that were well into the 70s and approaching 80 for a period of weeks. And then all of a sudden, after that period where trees were leafing out and everything was getting ready for spring, we had 2 days of fairly record-setting frost or extreme frost conditions, where those caused damage to all the trees that had just leafed out into the sensitive buds. And so that, at the time, was kind of termed the fall spring of 2012. And according to analyses done by folks from the USGS and the National Phenology Network, among others, they declared that the earliest spring in the North American record. Of course, I think 2017 will probably, once they have a chance to kind of look at the data more carefully, might actually be an earlier spring than that we saw in 2012. Nevertheless, that event had major implications for fruit trees across the Northeast and across the entire kind of north-central United States. In the Northeast alone, there were 100 counties that were declared disaster areas and included Northumberland County in Pennsylvania, which is where our experimental watershed is found. And so these fall springs can cause quite a bit of problems. especially as they promote kind of early budding and early leaf out in trees, and then all of a sudden you get hit with a hard frost. And the likelihood of these events, at least in the near term, is that they'll probably get more frequent, although the long-term projections from what I've read is that if the climate continues to warm, we'll see these events probably less frequently going forward. But in the near term, there's still a fairly sizable risk for these kinds of fall springs, which can obviously be fairly problematic. In terms of watershed hydrology, it's kind of interesting that, we're seeing divergent trends in precipitation and stream flow. So in terms of rainfall, our rainfall amounts are going up. We're getting more rainfall each year on average than we have in the past, a slightly increasing trend. So one would think that that would translate immediately to stream flow, that, we'd also have more stream flow. But oddly enough, our stream flow is actually going down. So even though we're getting more rainfall in, we're seeing less stream flow out, at least over the time period that we analyzed. Note that I'm expressing stream flow in millimeters, which is a depth. And the way we do that is we just take the volume of water that we get out of the watershed in, say, liters or cubic meters, and we divide that by the area of the watershed. So let's say it's cubic meters. We divide by the area of the watershed, a meter squared, and we're able to express stream flow as a depth. In meters, I can convert that to millimeters. And so that allows me to compare it to precipitation, which is also expressed as a depth. So we know we can do a water balance, basically. And you can see that there's a divergence, more rainfall, but not necessarily more stream flow. And so that has implications for, what we know as evapotranspiration, basically. So if we do a simple, we can look at the potential of evapotranspiration, and that can be done with physical equations or physical relationships. And just based on temperature and solar radiation, we can calculate that potential evapotranspiration has been going up. So that's just the absolute potential, that could be realized. Whereas what we measure in the watershed, how much rainfall we get in versus how much stream flow we get out, we see that, the actual amount of evapotranspiration is also going up. It's going up faster than the potential. So in a way, we're kind of increasing the efficiency of evapotranspiration. So the actual is actually getting it's getting closer to the theoretical maximum as we go forward in time. And so the reason that we're seeing increased evapotranspiration in this watershed is really due to the fact that we're extending our growing seasons, and trees are able to transpire over longer time frames now than they were in the past. And this mostly agrees with other studies across the Northeast U.S. There are some instances in New Hampshire, for example, where evapotranspiration is going down, and it's kind of a paradox to folks who do research on some of those watersheds. But by and large, across the Northeastern U.S., actual evapotranspiration is going up as the climate is warming. In terms of the seasonality of what we see, we see kind of some interesting differences in terms of when we get our rainfall increases and when we're getting our stream flow increases. And so when we look at this on a monthly basis, we're getting monthly rainfall increases mostly in January and also in the fall during October. Those are our big increases in rainfall that we're seeing. And some of the major decreases that we're seeing are in June and November. In terms of stream flow increases, the big increases that we get are in October, with substantial declines in February and July. So even though our annual stream flow is going down, there are some periods, some months, where we're seeing increasing trends in stream flow, particularly in the fall, and that's kind of the most interesting to us because that's also when we're seeing a big uptick in rainfall. And a lot of that has to do, not all of it, but a lot of it has to do with some of the larger storm events that we've been seeing in the fall over the past several years. Tropical Storm Lee is kind of the poster child for that, but not the only one to point out. But here's a slide showing Tropical Storm Lee in September 7-8 of 2011, which was a huge rainfall event that affected a good chunk of the eastern seaboard. This just shows where Mantango Creek is located, kind of right in the epicenter of some of the heaviest rainfall, where we got anywhere around the 14.5 inches of rain over the 2-day period, and hourly rainfall intensities on the order of 1.3 inches an hour. So a fairly extreme event. When we look at this time frame in general for the fall, we're seeing that indeed our hourly rainfall intensities are going up in the fall, and that our stream flows are going up in the fall. And so it's in part due to events like this that are it's kind of a drier time of year otherwise, but these big kinds of storms, these big storms can have a big influence on the amount of flow that we see out of our watersheds. And it's interesting because these events are largely driven by forces that are occurring well beyond kind of where we're seeing the extreme rains. And in the east, we get these phenomena called atmospheric rivers. I mean, you probably read about them in the news, especially related to California and all the extreme rainfalls that occurred in California this year that kind of brought them out of their drought. Those are tied to atmospheric rivers as well. We get them here in the east, and they often produce some of our worst flooding. Some of our worst floods can be tied to these kinds of atmospheric rivers. And so I'll just show you as an example, what these can do for, in a situation like with Tropical Storm Lee. So here is Tropical Storm Lee, and here's actually a hurricane here off the in the Atlantic Basin. And you'll see, I'll put this in motion, you'll see how these two systems kind of interact and produce kind of the moisture stream that produced our floods for Tropical Storm Lee. So when I put this in motion, you'll see, how these two systems kind of interact. And then if you zoom in, you can see these two atmospheric rivers that formed during Tropical Storm Lee, one coming out of the Gulf of Mexico here, and another one coming out of the Atlantic. And here we are in Pennsylvania getting all of this rain. This is precipitable water is what's shown here, but these are these atmospheric rivers that are producing these huge amounts of rainfall that we saw during Tropical Storm Lee. Even some of our local flash flooding can be driven by these kinds of events. Even some of the thunderstorm complexes that we've seen that have produced some of our flash floods recently are tied to these kind of events. And so there's research elsewhere, in Europe and in California showing that climate change is likely to increase the frequencies of these kinds of events. No such work's really been done on the East Coast that I know of, but it's likely to hypothesize at least that the same kind of phenomenon could increase here as we continue to warm the climate and the climate has more water vapor to work with for these kinds of storms. And so there's no doubt that Tropical Storm Lee's rainfall was extreme. It had an occurrence interval of about 980 years, or just shy of 1,000 years. So it's a fairly sizable event for those of us on the eastern seaboard. But even when you look at less extreme storms, ones that are occurring more every 50 to say 100 years, those are actually even increasing in frequency. And this is work that Art DeGaetano did out of Cornell, showing that in the Northeast, basically the take-home message is that what would have been expected to be a 100-year event based on 1950 to 1979 data now occurs with an average return interval of about 60 years. So basically the last year, or the 100-year event of the past is now a 60-year event. So it has a much greater probability of occurrence today than it did in the past. So even these less extreme storms are occurring with greater regularity excuse me, today. In terms of snow, we've seen a trend that kind of reflects what we've seen across the Northeast. We're just seeing fewer days with snow on the ground. So this is just days with snowfall on the ground for our experimental watershed. And the number of days with snow on the ground is going down. It's not to say that necessarily the snowfall amounts are increasing. Some years when we get these fairly sizable storms, you can actually have all of your snow in one event, but the number of days with snow on the ground has gone down. There's more days where the ground is bare or where you get snow and then it melts pretty quickly, and it's less likely to have snow cover that extends throughout the winter recently. And when we look at that in the context of floods, a lot of our larger floods in the past were driven by snowmelt runoff. And we're seeing a decline in that when we look at our data. This picture here shows the 1996 floods. So this is the big blizzard of 96, early in January of 1996, and then the floods that occurred a few weeks later. And basically what we've done, we've just tallied up our floods that we saw in our watershed that were due to rainfall and those that were due to snowmelt. And you can see in the 70s we had fairly equal distribution of rainfall and snowmelt-driven floods. But as we move forward kind of in the 2000s, we've had a precipitous drop in the number of floods that were driven by snowmelt, with really only one such event in the 90s and the 2000s. Most of our floods are now being generated by rainfall. There's just less snow on the ground, and we don't see as many snowmelt-driven flood events as we did in the past. And so to summarize, basically, it's from our perspective, just looking at our own data and thinking about them in the context of the broader changes, that you see relative to what's presented in the National Climate Assessment, it's clear that climate change is here. We see steadily rising temperatures, in our watersheds, lengthening growing seasons, and these are all consistent with a warming climate. When we look at the basin level, we see increasing evapotranspiration due to longer growing seasons, and this is probably the clearest change we've seen in our hydroclimate over the past 45 years. We're seeing larger, more intense rainstorms, particularly in the fall, that have led to augmented stream flow. And snowmelt runoff events are on the decline, at least as we look at our data from 2012 going backward to 1968 when we began monitoring. And so that's kind of like the local level, so we could kind of take a look here for the last maybe 15 minutes or so at what's gone on or what is projected for our climate future, if you will. So what are some of the models and what are some of the projections if we kind of don't change our emissions pathways? And to kind of kick this off, I think it's helpful to look at kind of the long term again. I opened up with the long term, and it's always helpful to kind of go back to the long term perspective, in terms of climate history. And this just shows the past, say, 20,000 years or so. And what I'll show here are some temperature reconstructions that have been done by various, major scientific studies, over the past, say, 20,000 years, where they've used various data sources to reconstruct temperatures, ice cores, and ocean sediments and things like that. And just to kind of lay the groundwork for this plot here, the green band is basically temperatures that we've seen for all of agricultural history. The orange kind of banded is kind of an area of temperatures that are really unknown to humans, ones that we haven't really experienced since humans have been around. And the red area is what most climate scientists would indicate as kind of the dangerous zone of climate interference, where we really don't want to go. And kind of on the bottom axis here is just kind of pointing out the last ice age, which kind of extended up until about 10,000 years ago. We saw the first cereal crops 10,000 years ago, and then intensive agriculture came on the scene about 5,000 or 6,000 years ago. And here we are, this is 2015 or so, thereabouts, and then this goes, several hundred or thousand years into the future, kind of thinking about the projections. And then so let's kind of put this in motion. This is a study by Shikun et al. In Nature showing how we're coming out of the last ice age and kind of warming into that region where we had, agriculture come on the scene. And you can see that we've had agriculture over this extended time frame here where temperatures have largely been in this green band, kind of this zone where fairly constant temperature over a very long time frame, really. And so that's what's allowed agriculture and civilization to kind of take hold. And so if you look at some of the projections, this is RCP 8.5. So this is our business as usual scenario according to the IPCC, with a carbon dioxide peak of 1,370 parts per million. And if you go well out into the future, this goes well beyond 2,100. But this is kind of gets us into a zone where we really don't want to be. And if we were to stabilize climate by reducing climate, say greenhouse emissions, and then this shows kind of the stabilization scenario. So, we really want to try to stay in this green zone, and we really don't want to get, too far out of, a zone where, agriculture, has come and had been able to kind of to flourish. So just kind of that lays the perspective, I think, for kind of where we are and where we could be headed. Kind of over the shorter term, let's look at some implications for the Northeast, kind of just thinking about, maybe into the mid-century. And so what we've done here is we've used downscale climate data from regional climate models that we have access to through Catherine Hayhoe and her colleagues at Texas Tech. There's 9 models that we had to work with. And some of the maps that I'll show you for the Northeast, we picked a model that was kind of middle of the road, like, not the warmest or not the coolest model, but one that was kind of in the middle in terms of looking at the projections for our business as usual pathway. And so let's just take a look at temperatures. So the mid-Atlantic climate is temperate, currently. So we have mean annual temperatures that range from 40 to 58 degrees Fahrenheit. This just shows the distribution of temperatures throughout the Northeast U.S. And this little sidebar here shows the historical temperature range for the mid-Atlantic region, kind of a nice mean of about 50 degrees Fahrenheit or so. And then we can show how that's likely to change as we shift into middle of the century, so shifting from 2015 to 2044, and average temperatures over that time frame are likely to be warmer, shifting maybe to a mean of about 52 degrees Fahrenheit for the region. And it's just worth pointing out here that some of these southern regions actually get up to a mean of about 60 degrees Fahrenheit. I'd almost have to create another color to show the temperature increases for the southern part of the mid-Atlantic region. But essentially, we'll see warming, and kind of the types of changes that we're looking at are an increase of, say, 3 to 4 degrees Fahrenheit relative to the long-term mean. And that's just going out into the middle of the century. If we zoom into the Mantango Creek experimental watershed and kind of look at some downscale projections just for our basin, a warmer climate also means more extremes. And so if we look at some of the downscale data here, this band is just, these are the 9 climate models that we had to work with. The lower part of the band is the coolest extremes, and these are the warmest extremes, and this represents the mean projection going all the way out to 2100, and this just shows daily max temperatures at different time points. You'll see that in 1975, daily max temperature about 95 plus or minus 2 degrees Fahrenheit. If we go out to 2025, it could be anywhere, 98 plus or minus 7. And if we get far enough out, towards the end of the century, some of these climate models will print out daily maximum temperatures that could approach 108, and we could actually be as high as 110 or 111 by the end of the century. When you look at some of the ranges in temperatures that we could see for the mid-Atlantic, for the Pennsylvania portion of the mid-Atlantic region. So those are temperature extremes. If you think about growing seasons, again, they're likely to get longer. These are the current growing seasons, about 200 days or so when you kind of think of the average across the mid-Atlantic region. They're likely to get longer, approaching 240 days on average throughout the Northeast. And when we zoom into the Mantango Creek watershed, this just shows kind of the range in those 9 models and what growing seasons would be likely to look like as we go all the way out to 2100. And if you look at some of the models, these growing seasons are being calculated using temperature data, so maybe they might not be as long as what's shown here, but there's a potential that some of the growing seasons could extend, almost the entire year, not quite, but more than 320 to 350 days for this area of Pennsylvania. In line with that, frost days are likely to diminish, so there's, not surprisingly, as the climate warms, it's likely that you'll see fewer frost days as we go forward in towards 2100. And then in terms of rainfall, rainfall amounts are a little bit trickier for the models to get a handle on. The models do much better with temperature than they do with rainfall, but there's a lot of agreement that we'll get increases in annual rainfall. So right now we get about 42 inches of rain per year on average across the mid-Atlantic region. That's likely to go up to maybe 44 inches or so per year, with some regions seeing upwards of 50 inches per year. And so that leads to just a basic increase in rainfall across the entire region. So anywhere from 5 to 15% more rainfall on average annually than what we've seen in the past. If you take kind of this middle of the range climate model at face value. In terms of what we'll see in Mantango Creek, a lot of spread in the models. Like I said, they don't handle rainfall as well as they do temperature, but definitely consistent agreement that there's more likely to be more days with 1-inch rainfalls than what we've had in the past. So some consensus in that these 1-inch rainfalls are likely to increase. The days with 1 inch per day rainfalls likely to go up. Also, in terms of the more frequent or some of these more extreme events, so the kind of events that would produce maybe 5 inches a day, these would be a 20-year storm. They're likely to increase maybe by 3-fold in frequency as we get out to 2100, and this is based on data from the National Climate Assessment. So even an increase in some of these more extreme types of rainfall events. But kind of in a paradox, just because we'll get these more extreme rains doesn't mean that we're also not going to face drying. Interestingly enough, a lot of the models also suggest that the future will be drier. Even though our annual rainfall amounts are likely to go up, a lot of that's going to be driven by extremes. So a lot of the big events are going to produce most of our rainfall, and the periods of time in between those extreme rains are likely to be dry or drier. And so, interestingly, I'm sorry, here we go. So if you look at in the eastern U.S. here, you can see that a lot of the models actually predict longer dry spells, so longer periods of time without rainfall. Even though we'll be getting more rainfall annually, it's just that there'll be longer periods of time without rain. And so during those periods, you have quite a bit of evaporative demand. And so studies that have been done for kind of at the continental scale show drying almost everywhere. And so you'll get larger rainfalls, but then you'll get these longer periods of time without rain, which is going to actually be a little bit tougher for folks to deal with if this were to come to fruition, in the sense that, you'll have to deal with these longer dry spells either by, irrigating more frequently or other ways to kind of overcome these longer periods of dry weather where soils can be drier and you have crop and stress and things like that. So kind of to summarize, our climate is really on the move. And so I had an animation like this for Pennsylvania, and I kind of redid one showing this for Maryland. And this is taking some information basically from Climate Central, who use data from the IPCC and others to kind of project what our climates might look like should we not change our emissions. And this is going to show for Maryland how Maryland's summers and winters are likely to be different. It'll show basically what Maryland's climate is likely to look like if you were to put it kind of in motion. And this would be looking at Maryland's climate at the end of the 21st century. And so, if you take Baltimore as kind of a point, in Maryland, and you can project for Baltimore kind of what in terms of its current climate and where it's likely to go. Maryland's climate is likely to be a lot more in the summer like southern Texas by the end of the century. And so that's kind of an extreme case, but that's if we don't really change our emissions. That's kind of the projection for Baltimore, is that Baltimore's climate, by the end of the century is likely to be more like extreme southern Texas than it is to be like the climate that we have now. If you think about Baltimore winters and you look at the baseline temperature, the projection would be that Baltimore would be a lot more like southern Alabama. By the end of the century. And this, of course, is for the business as usual scenario. So it's important to point that out. This is if we don't change our emissions, this is what the climate in Maryland is likely to look like as we go into the future. And so just in terms of, where to get more information. So the Climate Hubs, which was an initiative of the past, administration, helped put out these workbooks, working with USDA, NRCS. There are climate adaptation workbooks. And hopefully the next presentation will kind of get into this a little bit more, like how folks can adapt to the changes they're already experiencing as well as the changes that are projected for regions in the Mid-Atlantic. But this workbook is courtesy of Dan Dosty, actually, and his colleagues at NRCS. It's available at this website here, and it's basically to help farmers and foresters think of ways that they can adapt to the climate extremes that they're currently experiencing, and it's tailored to your individual location, and it's a really great resource. And so it's available online, and they're kind of working to test this out this year, really, working with landowners and farmers to try to test how the workbook works, what folks like about it, what they can improve upon, and it's a really nice resource. If you're interested in tracking projected changes in climate, there's a variety of tools that are out there to use. If you're just interested in short-term climate changes, one of my favorites is just the Climate Prediction Center through NOAA. And so these go out weeks to 1 year in time span, and it allows you to look at basically monthly to seasonal forecasts of temperature or rainfall. So is temperature likely to be above normal or colder than normal? Are we likely to have above normal rainfall or below normal rainfall? You can look at drought. where drought currently exists, what the projections are for drought development or drought improvement, and things like that. So this is a really great resource, and you can look at these, like I said, these projections will go out days, like 6 to 10 days, 8 to 14 days, and then you can look at it seasonal all the way out to a year, and it's updated pretty regularly, so you can always come back and see how the forecasts are changing. I can also say that Cornell University, among other places in the Northeast, has developed a number of really useful decision support tools. They have a website called Climate Smart Farming, and they have a variety of tools on there for farmers, including irrigation schedulers. And a lot of folks have been using these with great success. They seem to really like the irrigation scheduling tools. They look at water deficits and are able to project out for your farm or a parcel of land, when you need to schedule irrigation, given the forecast, looking out, weeks in advance. And so it's a really helpful tool. They also have frost freeze indicators for those with fruit trees and who work in the winery, in the wine industry, things like that. So there are lots of helpful tools there. And then another resource is the U.S. Climate Resilience Toolkit, which I've had some experience with now. All kinds of great resources there, including directories to other kinds of decision support tools that are out there and studies that have been done for the Northeast region as well as throughout the United States. But one nice aspect is that you can put in your zip code and look at climate changes over the past, say, 100 or so years, going back to the 1800s. So you can look at how climate has changed for your locality over the past 100 years, and you can also then look at projections for climate change for your particular zip code going all the way out to 2100. So lots of ways to interact with the climate data going back in time as well as going forward. And so it's a really great resource that NOAA has put together, and I've had some experience working with it. We had a demonstration on it last week at a conference that I attended, and it's really, really helpful. And so these are some tools that are out there that folks can use. And with that, it's a few minutes to 3, and so I guess I'd like to end there and just acknowledge my colleagues at USDA who helped quite a bit with the long-term trends, as well as Ann Stoner, Catherine Hayhoe from Texas Tech, who helped us get the downscale climate data that I presented for our site in East Central Pennsylvania. And Haiming Liu, actually, he was a visiting scientist with us from China and helped us analyze the trend data that I presented. So with that, really happy to take any questions that folks might have. And if I can't answer them right now over the phone due to time constraints, more than happy to respond via email or or get in touch with me another way. That'd be great. Thank you.
Thank you so much, Dr. Buda. I think we still have a little bit of time for some questions to ask you. One of the first ones that came in all of the stats stated, how do the numbers account for the actual duration of the extremes during, say, a 24-hour period, a week period, a year? For example, in a 24-hour period, you have 14 hours of 50 to 60 degree temperatures and then 10 hours of 15 to 25. So how do you actually
for kind
find
of
that
record highs
then?
and record lows, or just because they can be, you can define extremes a variety of ways. Like record highs and record lows, these would be daily highs and lows, so it would be the highest daily temperature, and whether that sets a record for the day, and it's in the same context, it's the record minimum temperature for the day. But you can also look at monthly temperatures. Then it's basically the monthly average temperature is what they're looking at. So the average temperature for that month and how that relates to the long-term monthly average. So you average across all the months. So for the one slide that I showed where there were months setting the global monthly temperature record. So you basically would take the average temperature for the entire month of, say, May, and you would compare that to the average of all the Mays from 1800 all the way until present, and you would compare the average from the current May to the long-term mean, and you would see that it was the highest May on record relative to all the other average Mays that we've seen. So it's just different ways of expressing records and temperatures, just like the annual temperatures are basically the annual average temperature and compared to the annual average temperatures from previous years.
How often were you measuring temperatures? Hourly, minutes?
In our watershed, we measure temperature every 5 minutes. So it gives us a pretty good feel for the maximum and the minimum daily temperature on a given day because we're taking temperature readings pretty regularly. Essentially, our sensors are measuring temperature even more frequently, but then they're averaging that over the 5-minute interval and reporting that number. But yeah, essentially 5-minute temperature data, our precipitation data are 5-minute intervals, which gives us a pretty good sense for rainfall intensity. We can calculate it at the 5-minute level, at the hourly, level, or however we want to look at it. Most sites in the United States don't measure temperature as frequently as we do. You might be at 15-minute intervals for NOAA, for the National Weather Service, and other sites might be hourly. So we have some of the highest frequency temperature measurements of quite a lot that go back far, of any agency, say, in the country. So. And in fact, there's an effort now to look at rainfall intensities at the 5-minute level across all of our sites. There's 18 or so sites nationally, and we're looking at temperature trends across all those sites at the 5-minute level, which would be kind of unique because no one's reported on such trends to date.
All right, I think one more question. Someone asked, has the percent impervious surface remained constant in the subject watershed during the study period?
Yeah, there's been really no change of land and land management. And this is kind of a unique watershed in the sense that it's really it's either farmland or forest land. The ridges are forested, and the farmland has really. You can look at aerial photos of the site going all the way back to the 50s, 60s, and the fields have the same shapes. There's been really no change in management. We have a technician that goes out in the field. He's been going out since the 90s, but we've been doing this really since the watershed began in the 60s, but now we do it more regularly, going out and interviewing farmers and finding out, what crops they're planting and when they're applying manure. But essentially, there's been no change in management, and the impervious surfaces are restricted to a few minor rural roads, and there's really been no development. So it's unlike other places where indeed there's been, like if you go to any urban or suburban area where there's been a big shift in impervious surface, and not only are you getting increases in rainfall intensity, but you're superimposing that on impervious surfaces that convert a lot more of that rainfall to runoff. But no such trends have occurred in our basin. So hope that it answers that question.
All right, well, thank you so much. Again, due to time constraints, we're going to move on. I believe Dr. Buda said that you can email him if you have any further questions.